All right, so welcome back after a wellness day. I know it was not a significant break, but I hope that you guys took advantage of that just to relax a little bit, so that we have, some batteries getting recharged to carry us through to the end of the semester. Now, before I get into the operating systems lectures, I want to talk a little bit about exam 2 that has been graded and the grades have been published. So, it's, all in all, it's a very good news in terms of statistics for the exam 2. Uh, 14 students scored above a 91, so that's brilliant. 12 students scored between a 81 and 91, and then there were 4 between 71 and 81. The average of the exam was 89.4, a very high median, a very small standard deviation because everybody sort of did well in the second exam. Now, in case you have some grading related questions, if you want to do apply for a regrade request, please email me within a week. Regrade requests by email within 1 week. So if you have questions about your free response answers, or even the multiple choice, if you want to know more specifics, then you can just send me an email or ask me during office hours. That's fine. But these were the results. Uh, Good news across the board. So pretty good performance from you guys for the second exam. Questions or concerns at this point? This is regarding exam 2 statistics. These have been released. The grades have been released on Gradescope for you guys to take a look over there. Okay. Now let's talk about the final exam. So we have a final exam scheduled by the registrar, and it is on Tuesday, May 11th. It's sort of at the very end of the exam week. The exam week starts from 6th to 12th, I believe. So we are just 1 day shy of the last day of finals week. So it's on Tuesday, May 11th. The time scheduled by the registrar is from 11:30 p.m. a.m. to 2:30 p.m. It's a 3-hour slot that we got. But the closer we get to the final exam, I will talk more about the logistics about how it's going to be conducted. But at this point, I would like you guys to mark your calendars with this date. Right, so mark your calendars for CANOS final with this particular date, Tuesday, May 11th. Questions or concerns here? Like I said, the more details about the logistics of the final exam will be discussed uh, closer to the final exam. Our last day of classes is Monday, May 3rd. So we have quite a bit of time after Monday, May 3rd for the final exam to come in. So we can do a good review session and talk more about the logistics then. Okay, looks like you guys don't have questions. Let's start talking about operating systems. Everybody has used operating systems. Some of them were general purpose, some of them were on their smartphones. Let's start talking about OS, operating system. So this is sort of our second uh, uh, part of the course. We are going to move away from computer architecture to operating systems now. The textbook also changes. So the textbook for this content is going to be the 9th edition of operating systems. So the textbook is Operating System Concepts, 9th edition, and the authors are Silvershirts, Galvin and Gagne. So what I would highly recommend for this particular lecture is to read chapter 1 later today or during this week. And the reason is, during this lecture, there will be a lot of terminology that you will come across, lots of new words, lots of new concepts, and it's very difficult to sort of contain that into one lecture. So what I would highly recommend for this lecture is for you guys to be able to read chapter 1 of the textbook. Now let's start taking a look at what is an operating system, right? So it sits right here for us. It sits right in the middle of the computer hardware and a bunch of users trying to run their system or application programs, right? So everybody is sort of trying to access the computer hardware. I want the CPU. I want to read and write to memory. So all of that is computer hardware. So if you want to talk about what is in this computer hardware block, it is the CPU, it could be memory, and it could be I/O devices, input output devices, such as your keyboard, mouse, a monitor, a hard disk. So all of those things are sitting right at the bottom of this flowchart. And if suppose user 1 wants to access these shared hardware resources, there has to be some intermediary between all the users and the computer hardware. And that is what operating system is providing us. The operating system is a program that is functioning as an intermediary between a bunch of users trying to share the same physical hardware. Now, the operating system, just above that, it is hosting, or it is a platform for many programs. Some of those programs could be system programs, and some of them could be application programs. So application programs are user run applications such as compiler, assembler, text editor, web browser, whatever you may have. Even this WebEx meeting is an application program. So all of that is being hosted or being run on a platform, on a basis. What is that? That's the operating system. Now, operating systems themselves come in a variety of types, right? And they are suitable for various applications. So suppose you wanted to do, let's start talking about general purpose. If you wanted to do a general purpose computer, what operating systems are suitable for general purpose? Well, we have seen them many times, right? So we know Windows. That's sort of like the 75% of market share is Windows right now. That's a very famous operating system, but it's a general purpose operating system. And in the same theme, you have your Mac OS, you have a Linux operating system. So these are general purpose. So they are sort of best of all aspects of an operating system, right? So they do a good job in terms of keeping the size small. They do a good job in terms of protection. They do a good job in terms of allocating resources. So that they are more for a general purpose use. Now, for the smartphones, and everybody sort of is using a smartphone nowadays, an Android operating system that is specifically for embedded applications such as your smartphone. Android is a pretty common one. I think its market share is close to maybe 80%, right? And then you have, of course, the iOS on your iPhones. And apart from that, you will have a variety of different operating systems. For example, you will have a robot operating system suitable for applications in which a robot and automation is concerned. Then you will have RTOS, real-time operating systems. So these are sort of embedded applications. So what is going on over here? Well, the size needs to be very small. So the size of the operating system itself is pretty small. And it is trying to, one of the major things that they are trying to do is response time, right? Like, how can I quickly respond to things in real time? In terms of network operating systems, you will have distributed operating systems. sort of for networked applications such as cloud computing. You will have different set of operating systems. Um, so just a few examples just to give you guys a sense of where you might have seen an operating system. Let's move on. So essentially it's an intermediary, right? Like it's essentially an intermediary between the users trying to share the common hardware. Now, I want you guys to picture this. If suppose user 1 says I want to write something to the memory, and users 3 says no, I want to write something to the memory. User n says no, I want to write something to the memory. Now all these users are trying to write to the same memory, and if the operating system was not present, then how would there be a fair and efficient allocation of who gets to write to memory or who gets to read from memory? Right? You see that the users are sort of are going to have to do that by themselves, which is going to be very inefficient. The operating system is allowing us to play the cop there, right? It's like a traffic cop. Okay, you get the resource now, next you get the resource now, and so on. And it's trying to adjust those allocations based on size of the processes, based on the priority of the processes, whether it's a user application or whether it's a system call. It's trying to check on all those aspects of a process. All right, let's go on to the next slide. Over here we are talking about OS goals, operating system goals. It's going to be to make things easier, more convenient, right? So that's the first goal, to be able to execute or schedule user programs and make solving those problems easier. We talked about that. Many users are trying to share the same physical hardware, and that efficient and fair allocation of those resources makes the things easier as far as the users are concerned. The operating system is going to facilitate that. Make the computer convenient to use, right? So if I'm going for a general purpose application, then I want my operating system, such as Windows, to make my experience of using a computer very convenient. I don't want it to spend too much time handling interrupts. I want it to do it in such a way that it almost happens seamlessly as far as the user is concerned. I also wanted to protect certain resources in memory from other users that could use my computer. Again, all of that is happening behind the scenes, but the user is getting a very convenient view of how things are being done behind the scenes there. Protect the computer from other users, right? So not all users are going to be good users. Some of them may have bad intentions. Some of them may actually try to change the operating system itself, right? So if you think about where this operating system resides, it is actually going to reside in the main memory. Now, if it is in the main memory, what if we don't protect the operating system from all the users that could be using this computer? Well, then we are saying any user could go in and actually change the operating system itself, and they might not have good intentions, right? So if you want to protect your computer from other users, and that protection can be of different flavors, right? One is protect the operating system from bad users, or protect other users from the bad user. So there can be many different possibilities there. So a layer of protection, or many layers of protection. And then your overall goal is to also use the hardware efficiently. So let's try to go into more details about the operating systems next. Now, OS, when you look at operating system, you can think of it in two ways. One is as a resource allocator, or the other is as a control program. So when it is a resource allocator, we know that it has to manage all the resources, right? Which CPU cycles are going to be used by user 1? When can user 1 be able to write or read from memory, right? So all of those things are management of resources. So the operating system is going to essentially decide between conflicting requests. On what basis? Should I prefer a higher priority process? Should I prefer a system call versus a user call? all of those things, if they are conflicting, the operating system is going to be the intermediary so that there is an efficient and fair resource use. Now, when you look at the operating system in a control program, it is also controlling the execution of those programs to prevent errors and to prevent improper use of the computer. So this is more about how does it do the file management, how does it protect the operating system, how does it protect other users of the computer from bad users. So all of that goes as a that's operating system as a control program. Now there's one program that is running at all times on your computer, which is what is called a kernel. You will hear this word kernel a lot, because that's sort of the core of the operating system. That program is running at all times as long as your computer is active, right? It's powered on and it's running. That's the program that is running all the time. Everything else is either a system program, which essentially ships with the operating system, or it is going to be an application program, which maybe a user installs it on your on the operating system. So a system program is essentially a process that the operating system is. A system program is something that is being done on the behalf of the operating system, and that is usually shipped with the operating system itself. All right. Now there are various components to operating system, and these are sort of its main tasks. One is process management, the other main memory management, data storage or your secondary hard disk storage management, a protection system, networking, and user interface, right? So if you think about an operating system, you are essentially thinking about all these components. Now we are going to spend some time talking about each one of them in a little bit detail, but as we progress through lectures on operating systems, we will look at some aspects of process management, some aspects of main memory management, some aspects of data storage and protection in a little bit more detail as we go through. But today is going to be essentially an introduction to these components. So let's start with process management. What is a process? Well, it's a program in execution. A program itself is a passive entity, right? It's just there. It's not running. Now, if a program is running, then it's an active program, which is called a process. And you can easily track this, right? And many of you, I assume, might have done this, right? Like when you go and try to look at what are all the processes that are running on your Windows machine or a Linux machine or a Mac machine, you look at your computer system, like what are the processes that are running, and there are different commands to find out this information. Depends on the operating system, but it'll give you a process ID, which is a PID, right? This is the process ID associated with this process, and some of you might have seen that. Now, activities of the operating system involved in process management, what are they? One, to create or delete a particular process, right? Sometimes you might want to create new processes, and in the next lecture we'll try to see how we can use a fork user command system call to create new processes. Sometimes when we are done with that thread, we might want to delete that process. Sometimes when we don't have enough resources to run that process, we might choose to suspend it. And when we do have enough resources to continue execution of that process, we might want to resume that process. So all of these things are going under process management and are being facilitated by the operating system. Now, we definitely need a provision to for this process management to go on smoothly, which is to synchronize the processes. And one lecture we are going to have is going to be about how do you facilitate communication between two processes using pipes. That's what we are going to look at later on in the course. That's inter-process communication, or IPC. Next, main memory management. We only have one physical RAM. How are we going to share that RAM between different users? and how is the operating system playing a role, right? So the operating system is going to keep track of which parts of memory are currently being used and by whom, right? So process 1 uses main memory segment from here to here. Process 2 uses it from here to here. Process 3 uses it from here to here. And the operating system itself is going to reside in main memory from here to here, right? So which parts of memory are being used by which process, that is a job of operating system to manage and support. Decide which process is to load when the memory space becomes available, right? So suppose we have suspended a particular process because there were not enough resources to carry it out. You want to resume it. When you try to resume it, you may want to resume it when there is memory space available for you to resume. So you have to kind of load that process into memory again and then start working on it. To decide which process gets to do that, again, a job for memory management, which falls under the component of main memory management. Allocate and deallocate memory space as needed. Again, another thing that we are going to look at in detail later on. I've got new processors. They are of a bigger size, a higher priority. I need some space in memory. How am I going to allocate that? I am done with certain processes. I'm going to deallocate memory space for those processes. Some processes are have a lower priority. I'm going to deallocate space for them. So all of those things are also falling under this category. Next, data storage management. This is your secondary storage, right? So this is your the bigger storage, the bigger and slower storage. This itself can be classified into two management schemes. One is for file system management and the other is for mass storage. So under file system management, how is the operating system going about creating and deleting directories and files within those directories? Does it support the primitives to manipulate files and directories? How is the operating system ensuring that the storage is consistent and durable? All of those fall under the category of file system management. And the last lecture we are going to have on operating systems is going to focus specifically on file systems. Next one is mass storage management, in which you have certain blocks of main memory that are free. How do you allocate this? How do you manage that free space? Another component in data storage management. How do you allocate storage? How do you schedule disk usage, right? Which process gets to write to the hard disk when? All of those components are going into data storage management component of the operating system. More aspects of data storage management. One is the I/O subsystem, input-output subsystem, and in this, the I/O devices will be doing buffering, caching, or spooling in order to carry out that I/O data transfer. So buffering is essentially each I/O device will have a local buffer in its device controller. And when there is a data transfer to be done between the memory and the I/O device, that buffering space will be used in the device controller or the I/O controller. Caching is sort of the same concept as we looked at in the cache in the memory lectures, right? So something that is small but very near to the processor that is going to allow us to do very quick memory accesses. Spooling is something that you see in I/O devices, for example, for printers, right? So printers are usually put on a spool, which is essentially maintaining a queue of requests. Okay, there is one printer, 10 people are trying to print to it, and they would put in their request managed by a spool in the form of a queue, so that one prints after the other. Now, an I/O subsystem also has a general device driver, for example, a very generic USB device driver interface, or users might be able to install their own device specific drivers such that the communication can happen between various I/O devices and your operating system. Now, the responsibilities of this I/O subsystem is to interface other system components with the operating system. how does the operating system talk to a mouse? How does it talk to a keyboard? How does it talk to a monitor? So all of that is being handled by this IO subsystem, which is part of our data storage management. Manage those devices. If there is data to be transferred from the IO devices to the main memory of the computer, it's going to manage that data transfer. And it is also responsible to detect when that input output operation gets completed. And it is through interrupts. And we'll talk about how to handle interrupts in just a minute. Now let's talk about protection system. This is sort of a very important aspect of a operating system, where multiple users are trying to share the resources, and the resources could be CPU, it could be main memory, it could be IO devices. So what if a user has bad intentions and says, all right, I'm going to write my process in such a way that the CPU always is going to be busy working on my process, my task. So suppose I write an infinite loop, right? Like, okay, process one, user one is a bad user. He or she writes a infinite loop. Now what is going to happen? The CPU is a shared resource, but now the user has forced it to work on this particular process all the time. We need a mechanism or protection such that that never happens, or we have a way to deal with it when it happens. So maybe a timer, right? So when the timer expires, you transfer control back to the operating system. Again, this sort of concept could be for any shared resource. So for example, even in memory, there is a shared resource. Can we make sure that the user one, say process one, right? So process one doesn't access the memory region allocated to process 2, right? So that's protection in memory. So we need a mechanism to control access by programs, processes, or users to the system that are sharing all those resources. And the protection mechanism must distinguish between authorized and unauthorized usage. So, for example, if a certain resource is only meant for operating systems to carry out a system call, we are going to distinguish that as we are going to qualify that as an authorized access, and we should have some mechanism which distinguishes that from a user trying to do the same job as an unauthorized usage. We are going to need controls to specify. We are going to need to specify the controls to be imposed for this distinguishing between authorized and unauthorized usage, and also we also need a way to enforce that. Let's take a look at the next one here, which is networking and distributed systems. So if you have worked sort of in a research lab, then you might have gotten to use a server that was accessible through a network. So suppose you have a collection of processors that are available to the user via a distributed system. Let's see, hold on. Denzel says, when we say users, do you mean people or different programs using the hardware? I mean people. Right. So when I say users, I mean people. And so here, when I say user 1, user 2, user 3, I mean people, right? And they are running their own application programs. So the application programs are sitting over here. They are being controlled by user 1, user 2, user 3. So you know, if you think about what we typically see in like a personal computer setting, there is user 1 that is doing all of these things on an operating system using the computer hardware, right? That's sort of the one thing that we typically see. There is only one user trying to do this. But if you have, say, different user accounts on the same computer, then you have multiple users doing the same thing. And often what happens is that same computer hardware and the operating system could be used by many users at the same time. And this usually happens in a distributed environment. So when I say users, I'm talking about people. Where were we? we were here, right? So in a distributed system, we are trying to take advantage of all that processing power, but we are trying to do this via a network, maybe a local area network. And the reason why we are trying to do this is because there are other people in the same research group who are trying to execute their high intensity programs, right? Like very, very complex, time consuming and computing intensive tasks. They are trying to execute that. So there is a resource of loosely coupled processors, right? Multiple processors that are available to you through a communication network, and everybody is trying to use that, right? So because it's going to be very expensive for each user to have multiple processors. So put all of those put all of those coupled processors at one place, call it a server, and allow the users to access it using a network. That's usually what happens uh, when you have very intense tasks to complete. And you might have seen that if you are part of a research lab, then that's usually what ends up happening. Now, there are some other aspects to that, right? So, for example, do each user that is trying to access this communication network, and at the end the processors, do they get all the graphics, or do they just use sort of a command prompt to talk to that server? Usually you don't do all the importing of graphics, you just do a command line interface for those sort of applications. So this is something that I have done personally many times, where uh, I've run MATLAB programs in a parallel MATLAB environment on processors that I had access to on a network. And you guys are familiar with MATLAB. At some point, you might have had to use it. MATLAB is comes in typically with a graphical user interface. But when I did that particular application, I just had a command prompt, and I had to enter my MATLAB commands in, and I was able to take advantage of all those processors on a network. All right, so in this, your access is shared. All of this helps you do what? Well, it helps to speed up computation, the availability of the data, and it also enhances reliability. Because when you're doing this on a network, you can also have redundancy built into the system. Next, user interface to the operating system, also called as the face of the operating system. And the general user is going to be familiar with item number 2 here, which is the graphical user interface. Everybody has seen it, right? Whenever you have turned on your laptop, you might have seen a desktop view. That was the face of the operating system, or the GUI for operating system, and you were using your mouse and keyboard to interact with that user interface. It was developed mostly by Xerox and made popular by the famous Apple Macintosh. But there's an alternative to this, which is the command line interface, or the command interpreter that I was just alluding to, which is a program that reads and interprets control system statements. For example, the Unix shell, or it could be the terminal in Mac OS, or it could be the command prompt in Windows operating system, which is sort of a DOS based system. All of this is I'll give you a prompt, you write the commands, as opposed to you using a mouse and clicking on things. You just write the commands to carry out a particular operation. So this is either a part of the kernel, or it is a special program. So in the case of the Mac OS, the terminal is not a part of the kernel. It is part of the provided as a special program. Now over here in that shell, you can run commands, for example, like run, remove, move, copy, and so on. So if you have done any sort of Linux based programming, then you might have had to execute these commands in the command line interpreter. So that's your sort of your second type of user interface to the operating system. That's how you interact with it. Now let's talk about system operation. Where does it start? Where does all of it start? When you turn on your computer, where does it start? Where it starts with the bootstrap program. Now, bootstrap program is not the operating system, which is a pretty common misconception there. The bootstrap program is not the OS. Bootstrap program is essentially the door to the OS. So this is the program that is stored in the ROM, right? So a ROM, or read-only memory, is a non-volatile memory. So you take out the power, but the contents don't go away. They still remain there. So it's independent of power. Or this could be like electrically erasable and programmable ROM, EEPROM. So what that has is the bare bones of getting to a stage where the operating system can start. So this is the firmware. The bootstrap program is also called the firmware. So when you start the system, the firmware is what is loaded into the main memory of the computer. And from there, the operating system starts getting executed. But what does it do? Once the firmware gets uploaded, what happens? It just waits. The operating system waits for events. Events are usually interrupts. Somebody has to interrupt it. Those interrupts could be system calls, or it could be user interrupts, or it could be a IO interrupt. But until then, the operating system is sort of sitting idle, doing nothing. Right. So I've loaded the program. I've loaded it into the main memory in the space allocated for the operating system, and it is just going to sit there waiting for events to happen. Events are usually called interrupts, and interrupts are further classified into software as well as hardware interrupts. So software interrupts are also called a trap or an exception. Examples of software interrupts could be a system call. Again, a system call is something that is happening on behalf of the operating system. Or it could be a divide by zero error, or it could be a memory violation. If you're trying to access the memory allocated to process 2, but you are process 1, that's a memory violation. So all of those things are going to initiate a software interrupt. And then the operating system has to respond to that interrupt. And depending on what type of interrupt it is, there is a specific interrupt service routine for each of those interrupts. And the interrupts could also be hardware interrupt. And this could be, for example, to complete some IO, right? So, for example, you have hit a few keys on your keyboard, you have moved your mouse. All of these are sort of hardware interrupts. Now, the data transfer for IO completion for a keyboard and a mouse is very quick, and the amount of data transfer is very, very small. But it could also be pretty intense data transfer. So, for example, if you are trying to move a big chunk of files from your main memory to a portable hard drive, right? So what happens? Well, that's still an IO operation, input-output operation. But once it gets completed, it is going to raise a hardware interrupt. I'm done with it. So how do you handle interrupts? How does the operating system handle interrupts? The first thing that it's going to do is to save the state of the machine. So whatever registers I need to save, I'm going to save the current state of the machine, including the address of the instruction I am executing currently. I'm going to save all of that in main memory. Then I'm going to disable any new incoming interrupts because I'm trying to service the interrupt that I'm currently servicing. So disable any new incoming interrupts. Then the control is going to transfer to the interrupt service routine. So for each device specific interrupt, you will have a interrupt service routine. Again, part of some instructions written in a specific area in the memory, right? So these are going to be vector of addresses in memory one for each interrupt service routine. If you are trying to write some data into a portable hard disk, there is going to be an interrupt service routine handler to handle that data transfer. Now, once you get done with your ISRs, then the CPU restore the state of the CPU and go back to that interrupted address. So go back to executing the instructions where you stopped. An operating system hence is mostly interrupt driven, right? Until you actually do some interrupts, it's just going to be there. It's going to just stay there. Now those interrupts, again, like I said, could be software, could be hardware. Software interrupts are usually sort of system calls. Hardware interrupts are generally user interrupts. Now let's try to illustrate the interrupt. Now on this diagram, we have two timing diagrams, right? So the x-axis over here is time. One over here, we are monitoring the CPU. The bottom one over here, we are monitoring the IO device. Now, the CPU itself could either be executing a user process or it could be processing the IO interrupt or going through the interrupt service routine for that interrupt. When it is executing the user process, it is not, it's just doing that initially, right? Now, the IO device, which is sort of independent here, say it is idle for some time. Initial time it is idle. And at some time it says it writes the CPU writes a few registers to the IO controller of that particular IO device. IO controllers are also called as device controllers to initiate that input output operation. So that is going to happen over here. IO request was made. It is going to then transfer data between the IO device and the main memory of the computer. And at certain time, the transfer is done. Once the transfer gets done, it is going to let the CPU know that I am done with the transfer, and the CPU services will be interrupted. It will be interrupted to complete that IO, right? So when you're doing this transfer, the data is moving between the IO device and the local buffer. So an IO controller or a device controller has a few registers that we are writing to, but it also has a local buffer. So the transfer over here is initially between the IO device and the local buffer. Once it's done, we are going to interrupt the CPU to make sure that that IO is completed. So that's when the data transfer happens from the local buffer to the main memory. But only for a short duration of time, the CPU stops executing the user process and services that IO interrupt. Now, depending on the type of the IO interrupt, that time might be very short or it might be very long. For keyboards and mouse and those kind of things, that time is very, very short. And if you want to move like really big files to secondary storage, that might take a longer time. Now, so once that is done, we service the routine, right? So now during the time at which there was data transfer going on, for as far as the IO device is concerned, the CPU was not interrupted, right? So the CPU was sort of going about its own business, executing the user process during that time. Now there are two aspects of this which are classified as synchronous IO and asynchronous IO that we'll talk about in a little bit. One will be sort of generally faster than the other. Let's take a look at that. Now each IO device has a IO controller, also called as the device controller. Has registers, and it'll have a local buffer for that IO device. The CPU initiates the IO by writing specific registers in the IO controller. So the device controller has two things. One, registers that you can the CPU can write to, and the other is the local buffer. for data transfer. Now, when it writes those specific registers in the IO controller, then that's how the IO interrupt gets initiated, depending on what you're writing to those specific registers. The running process can now either do one of two things. One is wait for that input output operation to complete, which is what we are calling a synchronous IO. And at this time, and because we are waiting for that IO to complete, at most only one IO can be completed at one time. The other thing that we could do is proceed anyway. Just keep continuing to work on the user process, don't get interrupted. It is called the asynchronous input output operation. And in this, because we are proceeding anyway, more than one IO can interrupt at any given time. But because you have many of them trying to interrupt, you need a device status table to keep track of all the IO requests. So in one, you are waiting for the IO to complete. In the other, you are just going about your same business, ignoring the IO, but you are keeping track of it in a device status table. So a device status table is going to keep track of all the requests that are coming in. Let's talk about the device status table using this particular slide. So you have several devices over here, right? So there's a device card reader 1, line printer, disk unit 1, disk unit 2, disk unit 3, and so on. So all these are devices, and they are all labeled in a table format, and it also has a status entry. The status could either be busy, idle, or not functioning, right? So whenever there's an IO device trying to request for that IO transfer, it could be either idle, busy, or in the not functioning state, right? And requests as they are coming in, say for line printer, they are put in this table. Okay, so this line printer 3 is right now busy. It in the queue, it has a request for the line printer. The address in memory is listed, and the length of that particular request is also listed over there. Now, when you have multiple requests by the same IO device, then they are put in a form of a queue, right? So for disk unit 3, you have item 1 in the queue, item 2 in the queue. So all of those things are sort of maintained in a device status table. So you are servicing these IO requests not by stopping user processes, but you are just keeping track of these requests in one table. Now let's take a look at the difference between synchronous and asynchronous IO a little bit more. So in both these types of IO, you have the requesting process as the user process, right? So you have user at the top here, and everything else that is at the bottom here goes as part of the kernel. So the device driver, the interrupt handler, the actual hardware, all of those things are in the kernel space. The user is way at the top over here. So the user or the requesting process, say, initiates a data transfer to an IO, right? So that particular request is going to, through the device driver, the control is going to be transferred to the hardware where you're trying to do that data transfer. Between what and what? Well, between the local buffer and the IO device itself. Now, once the data transfer gets completed, you see all throughout that time, my requesting process is just waiting there, doing nothing. Once the data transfer is completed, through the interrupt handler, we are going to transfer control back to the requesting process so that it can continue. But the disadvantage over here is that all throughout the time at which the data transfer is taking place, that requesting process is simply waiting there, right, doing nothing. There is some good news and bad news here. The good news is I don't need to maintain any sort of table to know which IO device was requested, right? So which process was requesting, I don't need a table to tell me that, because there is only one at a time. However, in the case of async, the good news is I don't need to keep track of requesting process, but the bad news is that I have to wait for a very long duration of time. to go back to return to my requesting process. For asynchronous IO, similar things happen in the user space. There is a request, the IO request is made. You go to the data transfer, you go into your hardware, the data transfer gets completed between the local buffer and the IO device. But now you're not waiting, right? So what you're doing is essentially updating the registers in the device controller and then going back to the requesting process by just logging information into the device status table so that those requests can be later fulfilled, right? At a later time, they can be fulfilled. But every time you are updating that device status table, you're coming back to that requesting process. Once the data transfer gets completed eventually, you can also come back to the requesting process. So the transfer of control to the requesting process is immediate, right? So you see, the control is being transferred between user and a kernel space. So the user initiates it, but the kernel is not going to take too much time. It's going to return that control back to the user, having made entry into the device status table, so that it can be completed at a later time. But in this, we do need a device status table to keep track of who did what. Next, hardware protection. We need some way to protect operating system from the users and also users from bad users. So because sharing is something that we are interested in, it improves utilization. We want many users to share the same hardware resources. That's good. However, it requires mechanism for protection because there are many users involved. Some of them might not have good intentions, and we need some layers of protection in order to save the operating system as well as other good users. So one way to do this is a dual mode operation. I am currently in the user space versus I am currently in the kernel space. So that's what we call a dual mode operation. We'll take a look at an example about dual mode operation in just a minute. How do you protect IO? How do you protect your CPU resource? How do you protect memory spaces? We'll take a look at all these three items in just a minute. Dual mode operation, we simply have a mode bit. There's a hardware bit that is added to hardware to indicate the current mode. The current mode could be a kernel mode or it could be a user mode. So a user process, whenever the system is executing a user process, the user mode bit is set to 1. The mode bit over here is set to 1. So that we know we are right now working as a user in the user space. Now, as the user process is getting executed, maybe you are running a web browser, maybe you are typing on a word editor, right? So all of that is a user process getting executed. Suppose at some point there is a system call that is made. Again, system call is something that is to be done on behalf of the operating system. Very important, high priority, needs to be done for system to move forward. So suppose at some point we have a system call. Now a system call is done in the kernel space. So what we have is a trap or a software interrupt. The mode bit is changed to 0, right? And we go to a kernel mode. And in the kernel mode, we execute the system call. Whatever that system call was, we complete executing that system call. We change the mode bit back to 1, and then we return from the system call to the user space. So by just monitoring the mode bit, we will know whether you are in the user process versus in the kernel space, user space or kernel space. Now, what is the difference? Well, in one, you do not have access to everything. And in the other, the kernel space, you are going to be privileged because you can execute privileged instructions. So when an interrupt or fault occurs, the hardware switches from kernel mode is also called monitor mode, system mode, supervisor mode, or privileged mode. So when that interrupt happens, you go from user mode to kernel mode, complete that software interrupt, come back to the user space. By doing all of that, you're changing user bit, and by monitoring that mode bit, you know where you are. Where the privileged instructions you will not be able to do in the user space. You can only do that in the kernel mode. So now there is sort of a separation between system calls and user calls. So user calls cannot be high privilege calls. They can be to support a uh, user process getting executed. So let's take a look at how that system call to perform certain input output operation gets completed. So suppose you have you're right here, right? So some system call n has been initiated. Suppose you are in the user space. So in this diagram, what we have is in the gray over here, there is user space. Above that, there is a kernel space. This is space in the memory, for example. Now, when you're going through this system's user space, you have a system call n over here. So the process needs some input output operation to get completed. Right? Some request is being made. The control is transferred to the kernel space. Now we are going to choose what IO function we need to complete. So, and suppose we have a read input output function to complete. We are going to go there, execute that in kernel space, which is privileged, and then return the control back to the user. So start with user, switch to kernel, execute, return back to the user mode. Now in terms of IO protection and CPU protection, what are we trying to protect? We are trying to protect the operating system, and we are trying to protect other users. From what? From improper use of the IO devices. So privileged instructions that can be issued only by the kernel mode, all of those are privileged. All IO instructions are privileged. So for example, if you want to read or write from IO devices, they can only happen in the kernel space. So if you think about this, whenever you are typing something on the keyboard, that is a user initiating a data transfer, but the data transfer itself in the back end is being carried out in the kernel space. So all of those are privileged instructions. Now we also need mechanism to protect the CPU. Why is that? Well, some bad users might say, I will write an infinite loop and I will keep executing that infinite loop. I will never come out of it. Meaning I will simply hog the CPU resources all the time, so that no process, no other user can get the CPU resource. So of course, we need a way to regain control of the CPU. The operating system needs to regain control of the CPU so that it can meet one of its very basic functions, which is to do a efficient and fair allocation of resources. So this can be done by using a timer. So return control to the operating system, periodically issuing an interrupt. So whenever there is a timer countdown, so suppose the timer expires, you issue an interrupt. As soon as you issue an interrupt, the control goes back to the operating system. So if this can happen periodically, then no user can sort of take charge of the CPU for forever. Let's now talk about the third aspect. We talked about three things, right? Like there was a dual mode operation, then there was this IO protection and CPU protection. Now we'll take a look at how do you protect memory space that has been allocated for a process from other processes, right? So suppose you have this particular chart here showing you how the memory is organized. So suppose from certain memory address to certain other memory address, all of this is operating system. That's where the operating system is residing in the main memory. Then you have process 1, process 2, process 3, right? They have been given certain certain memory space has been allocated to each of those processes. Now, what we don't want is for process 1 to be able to read or write to process 2. Maybe we do for certain things, but in general we don't. And we don't want process 2 to get access to that or to access to that, right? All of the process 2 related things in terms of instructions have to fall over here. All of the things that are related to process 3 have to follow here, their data and instructions. Now, in order to keep those regions of memory protected, we will use 2 registers. They are called base and limit registers. So for each process, we are going to use a base register and a limit register to protect a region of memory from all the other processes. Right? So this way, we not only protect the operating system to be overwritten, right? So for example, one user comes in and says, all right, it looks like all the initial memory addresses are belonging to my operating system. I will go tweak certain aspects of the operating system in order to suit me, right? But you can't do that because the base and limit registers are going to protect that region of operating system. Nobody gets control over that. Process 1 gets it for process 1. Process 2 gets it for process 2 only. Process 3 gets it for only process 3. Now, base and limit registers are slightly different. One is the address of the starting point of the process. Limit is sort of base plus limit is your ending address, right? So the base address, if you see here, base is where does it start, and limit is actually the difference, right? So limit is essentially the length between the start and the stop and the start. So in other words, your stopping address is base plus limit. Now, how is it going to play out in terms of CPU generating an address that is belonging to a memory location that the CPU wants to read or write in order to work on a process, right? So suppose we have, say, let's mark these 1, 2, and 3. Right? So suppose CPU is right now working in process number 2, right? And it says, okay, I want to either read or write to a particular address in memory. And right now I'm working on process number 2. So it's going to generate an address. Because we have a base and limit registers that are used for protecting the region, that particular region for process 2, we are going to run 2 comparisons. One is the address, is it greater than or equal to the base register or not? And as you can see, if it is greater than the base register here, it belongs to process 2. So that's good. Yes, moves forward. No, initiates a trap addressing error to the operating system. That's a memory violation. Next, if it is yes, it is above the base. Now let's take a look at base plus limit. Base plus limit is essentially a stop, right? So let's mark that over here in maybe blue. Now that same address is now going to be checked whether it is less than base plus limit or not. So that is saying, is it here or not, right? It is less than that or not. If it is less, then that address can be used to access that location. If it is no, again, it's going to be a trap addressing error for the OS. So again, that's an interrupt, that's a software interrupt. The operating system is going to go to the interrupt service routine to handle that particular addressing error. So that's how you can use base and limit registers to protect processes from other processes, or even the operating system from other processes. All right, that is all I have for you guys. You guys can now do the activity number 19.